The purpose of section 4 is to show you how, depending on the function and where the zeros are and whether it has multiple zeros at the same point, how that affects the way the graph will look. For example, when the multiplicity for a 0 is just 1, then it's going to cross the x-axis once. When it is 2, then the graph will be tangent at that particular 0. And when it is 3, then the graph crosses the x-axis and is tangent to the x-axis at that 0. So if we look at the graphs below, and let's go ahead and zoom in a little bit so they're a little bit easier to read. So for instance, in this first graph, that function has 3 different real zeros. One of them is at x plus 1, one of them is at x minus 2, and one of them is at x minus 3. Note that the graph crosses the x-axis at one point on each case, and in fact, that also gives us additional information, which of course is that it has to have either a maximum or a relative maximum or a relative minimum between the 2 points. In other words, since we know that there are 2 zeros here, then that means that the graph has to have a maximum, a relative maximum in between, and then likewise has a relative minimum in between those 2 zeros. Here we have an example in which only one of the factors is real, because both of these will give me complex factors, and so it only crosses the x-axis once. And then in this third example, we have real zeros, but note that the x minus 1 factor, that's twice, and so what happens at x equals 1 is we actually have a tangent at that point, so it hits the x-axis and then rebounds, but it doesn't actually go through it. Whereas with the x plus 2, which is 3 times, it actually creates a little kind of saddle point at the x minus 2. And so depending on the multiplicity, you get different effects as well. Now, those 3 graphs were all with odd degree. In other words, here x cubed, that x cubed, and this one had x to the 5th. If we look at ones that have even degrees as their highest amount, so here is x to the 4th minus 5x squared plus 4, which has these as its factors, and so 4 different factors. And again, note that it crosses the x-axis 4 times, and that creates 3 spots that are relative minima or maxima. So here a maximum, relatively speaking, in this range, and then these 2 minima again. And then here we have an example in which this one is up to x to the 6th, and so you can see the various factors, and again, squared, so that's a multiplicity of 2, cubed, that's a multiplicity of 3, and so again we have that saddle point at x plus 1, and then we have it basically like a dip that is tangent, so it hits the x-axis at x minus 1, but then rebounds, and then for the one that just occurs one time, the graph goes right through it. So part of the point, let me zoom back out. Part of the point of this section is to show you patterns for what a graph will do at the different zeros depending on the multiplicity, but it also gives us a way to recognize or even graph or sketch a graph of a polynomial that has many terms in it if we know what the zeros are, without necessarily having to graph every single shall we say value on the graph, because we know that at certain points it's going to turn, At other points, it has to have a relative minima or maxima. At other points, it just has to keep going in the same direction after it crosses the x-axis. So, just to finalize, the polynomial function of degree n has at most n minus 1 turning points. So things such as this or this, those are turning points. With at least one turning point between each pair of successive zeros, the n behavior of a polynomial is determined by the dominating term, the term with the greatest degree. So for f of x equals 3x to the fourth minus 2x cubed plus 5x squared plus 6x minus 7, it has the same end behavior. And when we say end behavior, we're meaning at the end of the graph, as f of x equals 3x squared, 3x to the fourth. So even though this one has all these extra terms, the end behavior is dominated by that 3x to the fourth. And so it has to be the same, even though this obviously would complicate things such to have all those extra terms. Anyway, a sketch of a polynomial function as opposed to actually graphing it can be made by following the following steps. First, find the zeros of f of x and plot the corresponding x-intercepts. 2, find f of 0. This would be, of course, where it crosses the y-axis, and plot the y-intercept, and use end behavior, whether the graph crosses, bounces, or wiggles through the x-axis at the x-intercepts and the selected points as necessary to complete the graph. So again, step 1, find the zeros. Step 2, plot the corresponding x-intercepts. Find the y-intercept, step 2, and then use end behavior, whether the graph crosses, bounces, or wiggles through the x-axis at the x-intercepts and the selected points as necessary to complete the graph. Okay, there are two other ideas or concepts in this section. The first is called the intermediate value theorem. And basically it says if f of x is a polynomial function with only real coefficients, and if for real numbers a and b, the value is f of a, so you've plugged in a, you've evaluated f at a, and you evaluate the function f of x at b. If they are an opposite sign, then there exists at least one real zero between them. It's kind of like saying, if at this point I do an f of x of the function, it's going to be some negative value. Over here, it's going to be some positive value. So that means it has to cross the x-axis somewhere in between them. It does not necessarily tell me where that happens, just that there has to exist at least one real zero between the a and the b. And then the boundedness theorem says for a polynomial function of degree greater than 1, greater than or equal to 1, with real coefficients and a positive leading coefficient, dividing by x minus c, if c is greater than 0 and all numbers in the bottom row of the division are non-negative, then f of x has no 0 greater than c, and if c is less than 0 and the numbers in the bottom row of the division alternate in sign, with 0 being considered positive or negative, then f of x has no 0 less than c. Now, that one's a little bit difficult to appreciate just looking at the words, so when we look at an example in just a moment, it'll become clearer. All right, so what we want to do now is a couple of graphs. And first we're going to start off with graph this polynomial. So this is a cubic, x cubed plus 3x squared minus 3x subtract 15. If we used our p's and q's, note that the only factors here for the q is plus or minus 1. Here we have 1, 3, 5, and 15. If we were to go through all of those, it turns out that 3 is one of our zeros. So here, plugging in 3, fact, let's just do it up here. If we did f of 3, we would get 3 cubed, which is 27, plus 3 times 9, which is again 27, and then subtract 13 times 3, which would be subtract 39, and then subtract 15. So 27 and 27 is 54, 39 and 15 is negative 54, and so in fact this does equal a 0. So 3 is one of our zeros. And again, I did that using the P and Q that we were looking at from an earlier section. So let's go ahead and do some long division here now. If 3 is a 0, then x minus 3 is a factor. And so we're going to go x cubed plus 3x squared minus 13x minus 15. We know this is going to have no remainder because 3 was one of our zeros. And so we start off with x squared times x gives me x cubed minus 3x squared. And now we're going to subtract that row. So the x cubes are gone, and I have 3 subtract a negative, so that becomes 6x squared. Subtract 13x. So my next part will be plus 6x. 6x times x gives me the 6x squared. And then 6 times the 3, that will be negative 18x. The 6x squareds are gone, negative 13 plus 18. I'll put it right over here. I'll put it right here. So we're going to get 5x, subtract 15. And so when I do a plus 5, note 5 times x, that'll give me the 5x. 5 times the minus 3, that'll give me the minus 15. And so that will then have 0 remainder. So now I'm going to take the x squared plus 6x plus 5 equals 0. This one, in fact, factors into x plus 5 and x plus 1, which gives me zeros at x equals negative 5, negative 1, and of course we had 1 already at 3. So now I know where the zeros are. And then one more thing to check. If I plug in 0 for x, this will give me the y-intercept. So that's going to give me 0 and 0 and 0, and then the negative 15. So in terms of my graph, that means that the graph has to go through x is negative 5, which would be here. It has to go through x is negative 1, which is there. X is 3, which is there. And it has to cross the y-axis at minus 15. Now, in this particular case, just to double check or to give myself some more room, I'm going to do basically, this is 10 and 20 and 30 minus 10 minus 20, subtract 30. In that direction to give me a little bit more space up and down. That'll be 5, 10, 15, minus 5, minus 10, minus 15, like that. So that makes then the negative 15 to be right in here. So I know the graph goes through those points. Now, I'm going to do just a couple of more points to see what the graph is doing. So first off, I know that the graph is here at -1, here at 0 for the x's, and then this is at 3. So let's go ahead and try an f of 1. And if I put in f of 1, I'm going to get 1 cubed plus 3 times 1 squared minus 13 times 1, subtract 15. And this is going to be, let's see, 1 plus 3 is 4, minus 13 is minus 9, minus 9 minus 15 more, that's negative 24. So at 1, so here's 1, we're going to be at negative 24, which would be, let's see, 22, 24, that's going to be down here. Now, at f of 2, let's see, doing the same thing, so we're going to have 2 cubed plus 3 times 2 squared minus 13 times 2, subtract 15, so that's 8, that's 3, and times 4 is 12, so that's 20. 20 minus 26 is negative 26, and so that will give me a negative 21. So that's going to be right here, halfway between the 20 and 22, so that's this 21. If I don't want to do them all, but let's do f of 5. Doing the same kind of thing, it turns out that f of 5 equals 120. So note that by the time I get to here, to 5, even doubling these 10, 20, 30, 40, 120 is going to be way off the paper. So this one goes way up by the time you get there. If I did, since this is -1 and this is -5, if I did f of -3, turns out that is 24. So that would be 10, 20, 4, 2, 4. So let's see, we're going f of -3. So there's -3. So we're up there. And if I did f of -6, it turns out that's -45, which is below my graph. That's just 1 over, but I'm already off the graph. So basically, the general idea for this is I'm going to have a graph that kind of looks like this. It's going to go through that point. It's going to get very close to this one, and it has to come back down, go through these points here, and then come up. And of course, we already said that if you're doing f of 5, that's already over 120, so this one really takes off. But this is basically what a sketch of this graph would have to look like. And, I did a few points. 1, 2, 3, 4, 5. I did 5 extra points after I got my zeros and my y-intercept. But that's a pretty complicated graph that I was able to do, or at least sketch out pretty close with only the 5 points. And so that's part of the idea behind this, is using the patterns for what has to happen when you have zeros one time. I know it has to go here, it's got to come up and cross, and then it's got to come down here. I don't, explicitly know whether the maximum is right at -3, it could have been 3.5, but I don't need to do that. I know I'm pretty close to right here, I'm pretty close to right there, and then it's just gonna skyrocket in the two directions on the end. Now, in the second one, I've already got it all factored. So I have zeros at x equal 0, and that's twice. So that's going to give me a little satellite point. And then I also have zeros at x equals 5, x equals -3, and x equals 1. Notice how the signs are always opposite of what they were inside of the parentheses. So there are my zeros. So let's see, we got x is 5, that would be here. X is -3, 1, 2, 3, there. X is 0 twice, so we're going to go through a saddle there until we get to the x is 1. Now, let's see, let's try a couple other spots. If we do f of 3, so that'll get us halfway between 1 and 5 here. If we do f of 3, so we're going to get x squared, that'll be 9, and then 3 minus 5 would be -2, 3 plus 3, that would be 6, 3 minus 1, that would be 2, and that's going to equal -216. If we did f of -2, which is, right in this area, that one, it turns out, ends up equaling 84. If we did f of -5, that actually ends up being 3,000, -3,000. And if we did f of 6, that ends up being 1,620. You can go ahead and work all those out if you want to. So, it really falls off over here. It really skyrockets over there. Now, because those numbers get so big, instead of going by the tens that I did last time, now I'm going to go by hundreds. So 100, 200, 300, and so also -100, -200, -300. I'm still going to go by ones in this direction, so this would be +10, and that would be -10, so -5, and +5 there. So just plotting these extra points, let's see, 3 was -216. So that's let's see, that's 220 there. So not quite to that. So it's about there. And let's see, what else did I have? F of -2 was 84. So 1, 2, 10, 20, 40, 60, 84, just a little bit above the line there. So it has to be like that. And then the other ones are way off the page. So basically this one, it's going to be like something like this. It's really going to get steep. And then it has to come around through here. At least the relative maximum has to be close to here. The thing's going to have a little saddle. Come down here. And up. And then, at 6, we're at 1,600. So that really skyrockets there. So something like this will be my graph. And I would say it's more of a sketch than a graph. But the bottom line is, after finding the zeros, I just did 1, 2, 3, 4 extra values, and that gave me enough to get a pretty good look at what that graph will look like. Now, you're not probably going to have to do any graphs with my lab, but you'll have to be able to pick the right graph um, from the selection. And so, just getting the pattern, separate zeros, cross once, and a couple extra points. It's only 4 extra points, and I got a pretty complicated graph there. All right, so next we have a couple of examples that say using the intermediate value theorem to show that each polynomial has a real zero between the given numbers. So notice that they give us two numbers. Okay, we're gonna look at 2 and we're gonna look at 2.5. And basically the idea is one of them comes out positive and the other one comes out negative. Then we know it had to cross the y equals 0, the x-axis in between. So first off, let's look at f of 2. So 2 cubed minus 9 times 2 squared plus 2 plus 20. And it turns out that equals 2. And then we'll look at 2.5, which is 2 times 2.5 cubed minus 9 times 2.5 squared plus 2.5 plus 20. And this one actually equals negative 2.5. Now, by the way, this is coincidental that plugging in 2 gave us a 2 and plugging in 2.5 gave us a negative 2.5. All that's important is that since 2 and negative 2.5 have opposite signs, there is a 0 between x equals 2 and x equals 2.5. And so that's the idea. And basically what's going on, as we can see, since I went from 2 to negative 2.5, it was decreasing. So I went from 2 down to negative 2.5, so I had to cross 0 in between them. All right, here we have an example with two negative numbers put in there. So f of negative 1.8, well, that's going to give me negative 1.8 to the 5th plus 2 times negative 1.8 to the 4th plus negative 1.8 cubed plus 3. Use my calculator, and this one comes out negative 0.732. Plug in f of negative 1.7. Do the same kind of thing. And it turns out that this one equals 0.593. Now, honestly, I don't really care what those numbers came out. What I care about is opposite signs. I went from negative 7.732 to positive 0.593. Therefore, a 0 must exist. between x equals negative 1.8 and x equals negative 1.7. Where that could come in handy is if you were using a graphing calculator to actually make your graph for you. One of the hard parts of using a graphing calculator is you need to set the domain and range such that the graph actually shows up on your picture. And, if you had it that the zero had to be between these, then you could narrow that down so that you could actually try to estimate where that zero was from the graph. In this case, because we went from negative to positive, we would say it was increasing. All right, and then our last example here is show that the real zero satisfies the given conditions. This is going to go back to that part that talked about the bounded theorem. If you have a polynomial of degree n greater than or equal to 1 with real coefficients and a positive leading coefficient is divided by x minus c, and c is greater than 0, then all the numbers in the bottom row of the division are non-negative. Then the f of x has no 0 greater than c. So let's see what that means. Here, we want to see, are there no real zeros greater than 1? So what we're going to do is we're going to do our long division. And so we have 2x to the 5th, subtract x to the 4th, plus 2x cubed, minus 2x squared, 4x minus 4. Now we're going to do the long division. So we're going to start off with 2x to the 4th. So that'll give me 2x to the 5th, subtract 2x to the 4th. So the 2x to the 5th are gone, and I'm left with negative x to the 4th plus 2x to the 4th. So that's just going to be x to the 4th plus 2x cubed. So the next one will be plus x cubed. So x cubed and x will give me x to the 4th. X cubed times the minus 1 will give me subtract x cubed. So now I'm going to subtract those out. The x to the 4th will be gone. 2x cubed minus x cubed. Well, actually, 2x cubed subtract a negative becomes add. So that'll be 3x cubed. So now I need a 3x squared. So that'll give me 3x cubed minus 3x squared. The 3x cubes are gone. Negative 2 plus 3 brings me back to just x squared. Bring down the 4x. So now I need a x. X times x gives me the x squared. X times the negative 1 gives me subtract x. So the x squareds are gone. 4 subtract a negative makes it 5x. Bring down the 4. And so now I have a plus 5. So 5x subtract 5. Five x's are gone. Negative 4 plus a 5 gives me just a 1. So that's my remainder. So put that up here, plus 1 over x minus 1. So I'm going to rewrite the answer out, and we got 2x to the 4th plus x cubed plus 3x squared plus x plus 5 plus 1 over x minus 1. So there was the result. Now note, all of these terms have positive coefficients. So 2, 1, 3, 1, 5, this is plus again, they're all positive. Basically what the boundedness rule theorem says is if that happens, if we go ahead, we've tested whether or not we have a 0 at 1. Well, we got remainders, so that's not a 0. But because those all came out positive, that also tells us there are no real zeros greater than 1. So it can't be like 2 or 3 halves or 10 or anything else. It doesn't have any real zeros. The graph does not go through the x-axis at any value greater than 1. That's what that's telling us. So that is section 4.